Let me continue with some more operations that preserves convexity for sets in Rn. For two subsets omega 1 and omega 2 of Rn, the sum of omega 1 and omega 2 is defined as follows. This is a subset of Rn that contains all possible sums of elements of omega 1 and omega 2. So it contains all elements of the form W1 plus W2, where W1 belongs to omega 1 and W2 belongs to omega 2. Okay? Now, given a subset omega of Rn and a scalar alpha in R, we also define the product of alpha and omega by alpha times omega. This is the set that contains all elements of the form alpha times W, where W runs in omega. Okay? In the next proposition, we're going to show that if omega 1 and omega 2 are two convex sets in Rn, then the sum of omega 1 and omega 2 is also a convex set in Rn. And also, if omega is a convex set in Rn and alpha is a real number, then alpha times omega is also a convex set in Rn. Proposition. This proposition contains two parts. If omega 1 and omega 2 are convex sets in Rn, then the sum of omega 1 and omega 2 is convex. Okay, and in the second part, we have this. If omega is a convex set in Rn, and alpha is a real number, then alpha times omega is convex. So let me go through the proof of this proposition. I'm going to prove the first part and then leave the second part as an exercise. Okay? In order to prove the first part, I'm going to fix any x and y in the sum of omega 1 and omega 2. And lambda is a real number in the interval 0, 1. Okay? Then, because x is in the sum of omega 1 and omega 2, x can be represented as x1 plus x2, where x1 is in omega 1 and x2 is in omega 2. Okay, and similarly, y can be represented as y1 plus y2. Here y1 belongs to omega 1 and y2 belongs to omega 2. Okay, then if we look at lambda x plus lambda y, we have the following. Thus lambda x plus 1 minus lambda y is equal to lambda times x1 plus x2 plus 1 minus lambda times y1 plus y2. Okay, and this is equal to lambda x1 plus 1 minus lambda y1 plus lambda x2 plus 1 minus lambda y2. Okay, now because omega 1 is a convex set in Rn, and here we have that x1 is in omega 1, y1 is also in omega 1. So lambda x1 plus 1 minus lambda y1 is an element of omega 1. Similarly, because omega 2 is a convex set, lambda x2 plus 1 minus lambda y2 belongs to omega 2. Therefore, this element, lambda x plus 1 minus lambda y, can be represented as the sum of an element in omega 1 and an element in omega 2. So by the definition of the sum of two sets, this element belongs to omega 1 plus omega 2. So we have proved that if x and y are in this set and lambda is in the interval 0, 1, then lambda x plus 1 minus lambda y belongs to this set. Therefore, omega 1 plus omega 2 is convex. Alternatively, we can prove this proposition by using the fact that the direct image of a convex set via an R-phi mapping is always convex. As we can see in this figure, if omega 1 and omega 2 are two convex sets in Rn, then the intersection of omega 1 and omega 2 is a convex set in Rn. In the next proposition, I'm going to show that if we have a collection of convex sets in Rn, then the intersection of that collection is also a convex set in Rn. Let omega alpha, where alpha runs in I, be a family of convex sets in Rn. Then the intersection of omega alpha, where alpha runs in I, is a convex set in Rn. Okay, the proof of this proposition is very simple. It follows directly from the definition of convex sets. So I'm gonna fix any x and y in this set in the intersection of omega alpha, where alpha runs in I, and lambda in the interval 0, 1. Okay? Then x and y belongs to omega alpha for every alpha in I. Thus, because each omega alpha is a convex set, lambda x plus 1 minus lambda y belongs to omega alpha for every alpha in I. Therefore, lambda x plus 1 minus lambda y belongs to the intersection of omega alpha where alpha runs in I. So we have proved that if x and y are in this intersection and lambda is any number in between 0 and 1, then lambda x plus 1 minus lambda y belongs to this intersection, and so this intersection is a convex set. Now let me discuss a very important concept for convex analysis. Let W1, W2, Wm be elements of Rn. An element X of Rn is called a convex combination of W1, W2, Wm if X can be represented as the sum of lambda I, Wi, where I runs from 1 to m, where lambda I are greater than or equal to 0, and the sum of lambda I, where I runs from 1 to m, is equal to 1. Okay? For example, the element X represented as 1/3 W1 plus 1/3 W2 plus 1/3 W3 is a convex combination of W1, W2, and W3. Because in here, if we look at this coefficient, this is lambda 1, and this is lambda 2, and this is lambda 3. As we can see that lambda I, each lambda I here is greater than or equal to 0, and the sum of lambda I, where I runs from 1 to 3, is equal to 1. Therefore, by the definition, this element X is a convex combination of W1, W2, and W3. Okay. Next, I'm going to talk about a very, very important characterization for convexity of sets. Here we have a convex set omega. If we take 3 elements of omega, say W1, W2, and W3, Then if we form all convex combinations of W1, W2 and W3, we're going to have this triangle. Okay, for example, this is 1/3 W1 okay, and then in fact all convex combinations of W1, W2 and W3 form this triangle. And as we can see from this figure, this triangle is a subset of omega. In fact, we can show that if omega is a convex set, then all convex combinations of each element belong to omega. Okay, and the converse is also true. Okay, so in this proposition, we're going to see the following characterization of convexity. A subset omega of Rn is convex if and only if it contains all convex combinations of each elements. Okay, let me go ahead and give the detailed proof of this proposition. Okay, so in the first part of the proof, I'm going to show that if omega contains all convex combinations of each elements, then omega is convex. So this direction is easier to prove. So I'm going to go through each proof first. So suppose that omega contains all convex combinations of its elements. Our goal now is to show that omega is convex, and we're going to use the definition of convexity for omega. So we fix any x and y in omega as usual, and lambda in the interval 0, 1. Okay. Then we look at this element lambda x plus 1 minus lambda y. Okay. Now, if we let lambda 1 by lambda and lambda 2 by 1 minus lambda, then we can see that lambda 1 and lambda 2 are both greater than or equal to 0. At the same time, the sum of lambda 1 and lambda 2 is lambda plus 1 minus lambda, so it's equal to 1. Therefore, this is a convex combination of x and y, which are two elements of omega. Therefore, by the assumption here, omega contains all convex combinations of its elements, lambda x plus 1 minus lambda y belongs to omega. So this element belongs to omega because it is a convex combination of x and y in omega. Therefore, omega is convex. So this implication is very obvious. Now I'm going to discuss the forward direction for the proposition. That means here we assume that omega is convex. And then we have to show that omega contains all convex combinations of each element. Okay, and as we saw earlier, this is very straightforward from this figure. Now, if we take an element, for example, W1 in omega, or convex combination of one element of omega 1 is just omega 1. So it is in omega. Now, if we take two elements, W1 and W2 in omega, and we form all convex combinations of W1 and W2, we're going to have this line segment. Okay? Then it is also a subset of omega by the definition of convexity for set. If we take three elements W1, W2, and W3 in omega, then all convex combinations of these elements forms this triangle, and then it is also a subset of omega. Similarly, if we take all convex combinations of four elements of of omega, then we still have a subset of omega. So we're gonna prove this by using induction. Okay. Suppose that omega is convex. We will show that omega contains all convex combinations of its elements. Okay, so the conclusion is obvious for all convex combinations of one or two elements of omega. Okay. For example, if we only have one element W1 in omega, then a convex combination of W1, as you can see, is just lambda 1 times W1. And because the sum of the coefficient should be 1, then lambda 1 here is equal to 1. So this is just W1, and therefore it is in omega trivially. Now if we look at all convex combinations of two elements of omega of the form lambda 1 W1 plus lambda 2 W2, where both W1 and W2 are in omega. We can see that here, because lambda 1 plus lambda 2 is equal to 1, then this is just lambda 1 times W1 plus 1 minus lambda 1 times W2. And by the definition of convexity of omega, this is lambda 1 W1 plus 1 minus lambda W2. So as we see earlier, this is in omega. Okay, so this is obvious. Okay, now suppose that omega contains all convex combinations of k elements of omega. Here k is greater than or equal to 2. Okay. Our goal is to show that omega contains all convex combinations of k plus 1 elements of omega. Let us show that. Omega contains all convex combinations of k plus 1 elements of omega. And therefore, by induction, omega contains all convex combinations of it and its elements. Okay, so we fix any W1, W2, Wk, and Wk plus 1 in omega, and lambda I greater than or equal to 0 with the sum of lambda I, where I runs from 1 to k plus 1, is equal to 1. Okay, and then we form the following element from this element y, which is the sum of lambda I wi, where I runs from 1 to k plus 1. Okay, so this is just lambda 1 w1 plus so on, plus lambda k wk plus lambda k plus 1 wk plus 1. Okay, so this is a convex combination of k plus 1 elements of omega, and our goal is to show that this element y belongs to omega. Okay, so we have the following. From this equation, we can write it as the sum of lambda I, where I runs from 1 to k, is equal to 1 minus lambda k plus 1. Okay, and we're going to look at two cases. Case 1, this case is very trivial. In this case, we suppose that lambda k plus 1 is equal to 1. Okay, so in this case, 1 minus lambda k plus 1, then in this case 1 minus lambda k plus 1 is equal to 0. Okay, and now, so this is 0, and as we can see that the sum of lambda I, where I runs from 1 to k, is equal to 0, and each lambda I is greater than or equal to 0, the sum is 0. So then in this situation, each lambda I is equal to 0, okay, where I runs from 1 to k. Okay, so in this situation, so y is actually, because it's this sum, and as we can see from here, y is equal to wk plus 1, which is in omega. Okay, so in the first case, we show that y belongs to omega. Okay, now let's move on to the second case. Okay, in the second case, we suppose that lambda k plus 1 is strictly less than 1, and obviously it is greater than or equal to 0. In this case, 1 minus lambda k plus 1 is non-zero. Okay, then we have the following equation, since the sum of lambda I, where I runs from 1 to k, is equal to 1 minus lambda k plus 1, we can rewrite it by dividing both sides by 1 minus lambda k plus 1 as follows. The sum of lambda I over 1 minus lambda k plus 1, where I runs from 1 to k, is equal to 1. Okay? And we can denote each element here by alpha I. Okay. Then the element y represented by this formula can be written as follows. Then y is equal to the sum of lambda I wi, where I runs from 1 to k, plus lambda k plus 1 times wk plus 1. Okay. So this is equal to, I'm going to multiply the first term by 1 minus lambda k plus 1, and then divide by the same number. So this is just the sum of lambda I over 1 minus lambda k plus 1, where I runs from 1 to k. So this is just the same as this term. And this is the second term here, I keep the same. So this is lambda k plus 1 times wk plus 1. Okay. And over here, I forgot wi. Okay. Here I have to multiply by wi. Okay. So this is just alpha I. And we can see that the sum of alpha I here, where I runs from 1 to k, is equal to 1. So this sum is actually a convex combination of w1, w2, wk. And we know earlier that by the induction hypothesis, omega contains all convex combinations of k elements of omega. So this is a convex combination of k elements of omega. So this element belongs to omega. Okay. So I can denote this element by z. So this element is denoted by z, and we can see that g belongs to omega. Okay. So now y is written as 1 minus lambda k plus 1 times z plus lambda k plus 1 times wk plus 1. And note that g belongs to omega and wk plus 1 also belongs to omega. Therefore, y is a convex combination of two elements of omega. And as we see earlier, because omega is convex, it contains all convex combinations of two elements of omega. Therefore, this element y, so y belongs to omega. We have completed the proof that any convex combinations of k plus 1 elements of omega belongs to omega. By induction, omega contains all convex combinations of its elements, and the proof is complete.